Right, hello and welcome back to another video. And as you've read the title, this video is about catalysts. It will talk about the chemical catalysts and the biological catalysts. I mean, they're probably quite similar, but they do have different processes in terms of how they work. And I'd say these are slightly more complex, and these are slightly more complex in their own specific ways. So before we dive right into what catalysts are and how they are used and how they work, I would like to just say please like and subscribe to this channel if you do think that this video will be in any way interesting to you, because I do talk a lot about biology and I will be talking a lot more about chemistry. People think it's more boring, but I'd say biology is more interesting. I'm just more a biology person, but I will be doing a lot more videos on chemistry in the future because I do think that it's a very interesting topic. So let's dive right in. Sorry if I'm leaning over. I just if I stood up on full height, I'd look at that. That's crazy. That's insane. Right? Okay. Sorry about that. So yeah, I don't have bad posture. I'm just leaning over because I wouldn't be fitting the frame otherwise. So let's dive right in. Um, Catalysts. I'm going to start with the chemical type of catalysts because these are probably slightly more interesting in terms of how they actually work. So here you've got something called a Boltzmann curve. A Boltzmann, I'm pretty sure, is like some kind of chemist from like some European country in like the 19th century or something like that. But that doesn't really matter. But basically, what he did was he created this extremely complex formula that takes in all of these different values, and it out the other side it comes out with this graph which shows how, because when you heat something up, not all of the particles, like let's say you boil water, not all of the particles are going to be boiling. It basically tells you the amount of particles that are at a specific energy level. Have I done this the right way around? Yeah. It shows the amount of particles that are at a specific energy level at, like, so let's say at a specific temperature. So this is the Boltzmann curve for just normal temperature. I don't know what that normal temperature is, but if it was I'll just do this. This is slightly unrelated to the actual fact of catalysts, but it kind of goes to show if you had a colder temperature, then it would be a bit closer to that. Yeah. If you had a warmer temperature, it would be a bit closer to that. But that's not really what we're looking at today. We're looking at the effect of catalysts. So, if you know anything about chemistry, then you would know that the activation energy of a reaction is the minimum amount of energy that is required for that reaction to occur, and it's also known as EA. So energy, that's the E, and then activation is the A. So this Boltzmann curve, the area underneath a Boltzmann curve shows the number of particles that are at or exceeding a specific energy level. Therefore, a catalyst, which will decrease the activation energy, and I'll get onto why in a minute, but a catalyst will decrease the activation energy, therefore making it so that there are more particles that have greater than or equal to activation energy. This new activation energy is called EC, E for energy, C for catalyst. So the more number of particles will have the required energy, or more than the required energy, and then this area under the graph between EC and EA shows the actual increase. And because there's an increase, it means that there is a higher rate of reaction because there are more frequent successful collisions. That's more about collision theory, and I will do a video on that another day. This is all very interesting, but I'm specifically talking about catalysts. But you just have to know with catalysts, in terms of chemical reactions, that the more collisions that there are, the higher the rate of reaction, the more successful collisions. Yeah, because particles need to have the correct energy when they're colliding to actually react with each other. So there are more number of particles that have the required energy, but how, you might ask? If you have any understanding of chemistry whatsoever, then you've probably heard the definition that catalysts are things that are not used up in reactions, and they lower the activation energy. And although this is slightly true, it is slightly disingenuous in the fact that they are used up, but they are regenerated, because the real true definition, I mean, probably not the true definition of catalyst, because the higher advanced you go, the complexer the definitions are. But the definition that is probably most relevant is that catalysts are things that are used up, but they are regenerated, because catalysts lower the activation energy by providing a different reaction pathway, which provides a lower activation energy than the original reaction pathway. I could show a nice little enthalpy graph here, but you can just assume that, let's say this is the activation energy normally, it's going all the way up here, and activation energy with a catalyst would be more like that. So instead of being like, what? It's more like that. So it's less, you need less energy. Because the activation energy, this is really basic chemistry here, and you probably shouldn't be watching this video if you don't know what activation energy is, but the activation energy is the difference between energy level of the reactants. Let's say this, my hand right here is the reactants, and the peak energy, so the difference between there and there is the activation energy, because it's the energy needed to start the reaction, basically. And a lot of the time, in a lot of manufacturing processes, you want to have the activation energy lowered so that you don't have to spend as much on energy, and therefore you can lower your profits. And I'll talk about that more towards the end of this section. So, how do catalysts actually work? Well, I said that they provide a different reaction pathway, but how does this separate reaction pathway actually work? So, you've got A plus B, where A is just the reactant and B is the catalyst, as highlighted. This arrow, it takes you to the product, where you have got the desired product, and also an intermediate. Intermediates are the opposite of catalysts, as you will see in a minute, because when intermediates are created and then they are used up, catalysts are not used up. I mean, they are regenerated, but intermediates are created and then used up, and catalysts are used up and then regenerated. So yeah. So you've got this intermediate, and then this intermediate will go, and it will be used up again, and this time the catalyst will come back and the product will stay. So the catalyst, it's been regenerated and the product is there, and this has all lowered the activation energy, and this is good. And if you want to do it mathematically to see that there's no like conservation of mass and conservation of energy, you can see that if you add up all of the reactants, A, B, C, and D, A, B, C, and D, then it will go to C, D, B, D, which is C, D, and there. And then if you cross off the things that appear on both sides, then you'll go A to D, which is what you can see here if we get rid of the catalysts and the intermediates, which is what we don't really need. I will just circle that intermediate there, just so it's a little bit clearer. So yeah, why are catalysts used in processes in manufacturing? Well, catalysts are used in processes in manufacturing because, as I said earlier, they lower the activation energy by providing a different reaction pathway, which means that there are more particles that have greater than or equal to an energy of activation. This means that you don't have to spend as much money on energy, which is used to like heat up the reactants to make sure they're at the right temperature. It also means that you can have a safer work environment because it doesn't have to be as hot. You might not have to use the same amount of pressure, which means that you'll have a safer working environment, you'll have a cheaper working environment, and overall catalysts are very useful. They must be a multi-billion-pound industry, multi-billion-dollar industry worldwide. They're very important, and it's a growing field. People are obviously trying to work about this. I wouldn't personally want to do this. It's slightly too boring for me. But yeah, it's a very popular field of chemistry. And yeah. Now, biological catalysts. You've probably heard of biological catalysts as enzymes, and that is what I will be talking about here. So, what are enzymes? Enzymes are proteins, which means that they are made of amino acids. Everybody knows what amino acid is, but if you don't, it's basically got like it's what makes up polypeptides, also known as proteins, because it has peptide bonds between amino acids, which create a polypeptide chain. This polypeptide chain, that's the primary structure, and then you've got the secondary structure, which has the hydrogen bonds, which creates the alpha alpha helix something, or the beta pleated sheet. And then in the 3D tertiary structure, which is the main part of the enzyme, then you have got the disulfide bridges, hydrogen bonds, ionic bonds, and they can create the specific 3D tertiary structure which makes up the active site of the enzyme. So that is the protein structure of an enzyme. Enzymes are proteins. So yeah, the specific 3D tertiary structure of an enzyme is complementary to the substrate. This little thing here is called a substrate. So it binds to the enzyme, and as suggested by the induced model of enzyme action, the enzyme slightly changes shape, which puts pressure on the bonds that are in the substrate, and therefore lowering the activation energy required to break those bonds that are in the substrate. And therefore, when the enzyme substrate complex is formed, which is what I just mentioned here, this is an enzyme substrate complex, those bonds are weakened, they're easier to break, and then the enzyme is catalyzed. The reaction is catalyzed by the enzyme, and the substrate is split, or the substrate is joined. Most enzymes you've probably heard of, they're going to split it, like amylase, that's going to split your starch. But there are also enzymes that can build bonds, such as DNA polymerase, which builds up the phosphodiester bonds between DNA nucleotides, and ATP synthase, which will build up the bonds between the inorganic phosphates in an N-adenine triphosphate molecule. But I just mainly included the diagram of breaking because breaking is slightly easier to understand than making. Yeah. And there are obviously different factors that affect the rate of enzyme action, such as temperature, pH, substrate concentration, enzyme concentration, but this video is already going to be for 14 minutes long, and I don't want to make it any longer, so you'll have to make do with that very basic explanation of enzyme action. I will probably make a video on enzymes in depth in the future, but this was just in the context of catalyzation of specific reactions. So I thank you very much for clicking on this video, and if you've watched all the way to the end of this 14-minute long video, then I please do ask you to like, subscribe, check out, comment if I've got anything wrong. I reckon I probably have. This is some complex stuff that I'm not entirely sure on. But yeah, check out my channel, you'll find a lot of other biological related content, and you'll probably find some more chemistry related content in there in the future, as well as other biological related content and other topics as well. So yeah, check it out on the channel, like, subscribe, and I shall see you in the next one. Bye bye.